So let's look at this trajectory, which I mean a very precise situation. I take a real entry matrix, 2 by 2 matrix, let's say, so it gives particular linear transformation from R2 to R2, going by this matrix multiplication with matrix A over 2 by 1 column vector, let's say. Okay, and what I call trajectory here means you start with arbitrary initial point x0 in your real plane, and you keep applying this matrix transformation over the points, denote ax0 by x1, ax1 by x2, and etc. Then you just keep a track of all those coordinates or the geometry points of those xi, call it the trajectory of this dynamical system. Let's take an example. Start with diagonal matrix, and then obviously this tell you that this V1, V2 standard basis is particular both engine vectors of A with engine value 0.8 and 0.64 correspondingly, and so you could imagine this real plane, which I mean each point is corresponding to a vector in R2, and just put the coordinate there. For example, 1, 0 is here, this is your V1. Okay, so for example, you start with your x0 arbitrary, let's call this is 5, 0 for example. Then okay, you apply your ax, this will be just lambda 1 multiply with V1, it gives you 4, 0. So 4, 0 will be your x1, and then you can keep doing that. You have got closer and closer to 0. This gives you one trajectory. If you're starting with somewhere else, and you will see that you got another trajectory. By computation, you will see that you got xi closer and closer when your I increases. Okay. Similarly, if you got starting from negative x1, x2, then the absolute value is decreasing, and so again it will decrease to 0. And you see this point is kind of attracting all those trajectories to it, right? So we call this origin attractor. Because all the trajectories are towards 0. Okay, and so let's take an example of different nature. So if you see, even for this diagonal matrix, it's really dependent on your absolute value of this engine values, right? If your lambda 1, lambda 2 are positive, and you will see that. If I start very close to 0, then my x1 will increase because I multiply by real numbers bigger than 1, and then this is all the trajectories here. Another trajectory, which means you start with different x0. Okay, you always start with some x0. You could choose different x0, and then you apply weight to this new initial value, and you got your new trajectories. As you could see, this one everything is reaching far away from this origin. In that case, we call this origin repeller. And there's, as you could imagine, also third type. Let's take example. For example, a matrix is 1 is bigger than 1 is smaller than 1, then again this V1, V2, standard basis again. Value, so here it's start with x0 here because 2 is bigger than 1, you got x1, x2, this trajectory leaving this origin, but if you look at your second direction, you got x0, you got your vectors pointing to this origin, and if you got some x0 here, you will see that this trajectory will look like this. Basically, it's because the x1 coordinate would become bigger and bigger, and the x2 coordinate would become smaller and smaller, right? That's exactly what is happening. And in that case, we call this origin saddle point. Always the origin. I'm talking about the origin, okay? So, actually, the same phenomenon happens. You don't really need to take this diagonal matrix. Okay. Another example. So let's take a matrix which is not diagonal at the beginning, at least. Okay. But suppose it's diagonalizable, and then you could, by changing basis, you got it. Become diagonal matrix. And then by computation, you will see that you got EG vectors, V1 and V2, for example, these two vectors, and EG values corresponding to 2 and 0.5. And so, how would the trajectory look like? So let's first fix this direction 1 minus 1. I write this as straight line because if you start wherever, because it says positive and bigger than 1. No, sorry, not positive. We care about that. Absolute value. Absolute value is bigger than 1, which is 2. So we start as x0 here. And you'll see that we apply our a to just because it's the engine value, it's the engine vector we want. It will just multiply by 2 over it. So it will become bigger and bigger. You are leaving. Similarly, if you start with some x0 here, you'll get far away. While if you look at this 1, 1 direction, because this absolute value is smaller than 1, if you got some initial point far away, it will become smaller and smaller, the absolute value, and so this is the trajectory towards the origin. Okay, and in the middle, if you have some x0 initial point here, and so you compute. So basically, what happens with it's very similar situation. So towards this direction, let's go with 2 direction, it will become smaller and smaller, while towards this 1 direction, it will become bigger and bigger, and so it will like this if you compute the points. Okay. It's like just changing this is similar phenomenon. Okay. What is more interesting is when our matrix has complex eigenvalues. Let's take an example. And you compute, you will see that you have eigenvalues. Complex number with b not equal to 0. So lambda 2 would be just lambda 1 bar, 0.9 minus 0.2i, and you got some eigenvectors. And so the corresponding eigenvector would be its conjugate. Okay, so how would the trajectory look like? We're still talking about real vectors. Start with some x0, and then you compute the iteration. So actually, we have already explained in the last exercise why a rotation is involved in this case, right? And we know that there will be some rotation phenomenon appears. So let's just give you some numerical results. So if you start x is 0 here, you will got basically something like this. So you're becoming a rotation. So argument is changing. There is a rotation. Secondly, the length is changing, right? Because it's a rotation and scaling. If you start here, got another example. Something like that. If you start here, so if you put direction, it will be like this. Similarly, direction like this. Here's another example. Okay, so the similar thing could be discussed for linear systems of differential equations, which I mean that if you got let's just still take the case this is a 2x2 real matrix, matrix, and so this is just 2x1 vector of functions, differentiable functions of t, and so this is just its derivative. Okay, so we can still talk about the trajectory. So let's take an example. Let's just take one example to show this. So we know that a particular solution, the solution set of this will be called, sometimes called fundamental set of solutions. So basically, if your A is 2 by 2 matrix, that solution set will be vector space of dimension 2, which means if you want to solve it, it's enough to find 2 linearly independent solutions. And the way we find it is we just, if it has 2 different eigenvalues, you just find 2 corresponding eigenvectors. It will give you, use it to construct 2 linearly independent solutions. So let's say the example. If your A is, okay, let's talk about this 2 by 2 matrix, and you will compute and say that you got 2 eigenvalues. One corresponds to the first eigenvalue, minus 0.5. Got a second eigenvector corresponding to lambda 2 equals minus 2, let's see. Okay, and then what I call trajectory, which means if you solve it, so your solution would be xt equals linear combination of these 2 fundamental solutions. The first is comes by construct from the form, it's always with the form eigenvector times eigenvalue t exponential. So this corresponds to linear combination of first and second fundamental solution. This will be the solution set. Okay, so trajectory for this system would mean that I start with, again, just initial point x0. So here my x0 would be, again, whatever you want. For example, you could start with, so let's say there is a direction with one direction, 1, 2. If I start with some x0 here, if we apply, so here I'm not saying that I'm going to multiplication by a. You could do that, but rather would I say that you just think of this as your x0, and then you increase your t from 0 to plus infinity, and then you keep track of where it goes. So here, when t goes to infinity, this goes to 0. So this is trajectory of this, like this. Similarly, you could imagine if you start with some x0 here, you would get closer and closer to 0. There is another direction with 2. Which is like this. Again, is the trajectory would pointing toward the origin. If you got some other x0, you would, by computation, you would see that the form and so again, this is actually a tractor of this origin. as you could imagine, you could also define what is called saddle point or repeller for different matrix A